At noon, ship A is 50 kilometers north of ship B. Ship A is traveling southwest at 24.2 kilometers per hour. Ship B is traveling due west at 17 kilometers per hour. Find the magnitude and direction of the velocity of B relative to A. So at noon, ship A is 50 kilometers north of ship B. So this distance is 50. So A is north of B. A is traveling southwest. So southwest means that the direction of the velocity of A is at 45 degrees to the horizontal. So west is to the left, of course, south is down. So southwest is between south and west, or an angle of 45 degrees to the horizontal. The magnitude of vector VA is 24 root 2, which is more than 24 units. I don't know what it is as a decimal. It's 24 by 1.4 roughly. The velocity of ship B is 17 kilometers per hour in a westerly direction. So the magnitude of this vector is 17, and it's pointing to the left. So this is the situation at noon. So this is when the timer starts. T equals 0. So at t equals 0, A is here, and at t equals 0, B is here. A is north of B. To get the velocity of B relative to A, we're going to write VA and VB in terms of I and J basis vectors. So I'm showing VA over here in the IJ plane. We want its I and J components. You can see that its I component is going to be negative. It's a vector pointing in the negative I direction. Its J component is also negative. Its J component is pointing in the negative J direction. So we see that VA is got by, first of all, looking at the I component, which is the magnitude of VA, 24 root 2, times the cos of 45 degrees. And of course, it's negative, don't forget the minus sign. So these two components must add by the triangle law. This I component plus the J component must give vector VA. So I'm using the triangle law here. The J component is also negative, so it's the magnitude 24 root 2 times the sine of 45 degrees. So all we're doing is just putting the two components together by the triangle law. The velocity of B is straightforward. It has no J component because ship B is going west. Its speed is 17, so its velocity is minus 17I. We are interested in the velocity of B relative to A. That's written as VBA, and we know that VBA, the relative velocity vector, is VB minus VA. So this is our key formula. So we have to take VB, which is minus 17I, and subtract this vector here. So we take the I component of VB, which is minus 17, and we have to subtract the I component of VA, which is minus 24 root 2 cos 45. So when we subtract this, we have a minus minus, two minuses here, giving a plus 24 times the square root of 2 times the cos of 45 degrees. So we have to work all this out, and works out to 7. So the I component of VBA is 7I. Now what about the J component? Well, the J component of VB is 0. See, it's minus 17I plus 0J, so it's 0 minus this J component here. That's going to give us plus 24 root 2 sine 45. That gives us 24. So we get plus 24J. So just subtracting the two vectors. We want the magnitude of VBA. We can write it like this. We could also write VBA without an arrow. But that could be confusing, because if we're talking about one-dimensional motion, VBA without an arrow could be positive or negative. we want to ensure that we get a positive quantity, so I won't use that notation because that's a bit confusing actually. We saw that in one-dimensional motion. We're dealing with two-dimensional motion here, as a matter of fact, so I suppose I could have used it, but I think it's better just to emphasize that we're dealing with a magnitude. We're going to be getting the speed of B relative to A. That's going to be a positive quantity. So we want the magnitude of this vector. And to get the magnitude of a vector, we just use Pythagoras' theorem. So we square the two components, sum them, and take the square root. If we do that, we get 25. And the units of speed here are kilometers per hour. Now, we also want the direction of the velocity of B relative to A. The axes x prime, y prime are moving with ship A. So where A is at the origin of these moving axes. So B appears to be moving with this velocity here. So I will show VBA on this diagram. Its I component is positive, J component is positive, so it looks something like this. This is VBA. So to get the direction that B appears to be moving in from A's point of view, we could get this angle here. So B appears to move along this line. This is the trajectory of B, ship B, as seen from ship A. So we use the fact that the tan of theta is opposite over adjacent. The side opposite is 24 units. The adjacent is 7 units. So tan of theta is 24 over 7. Theta is inverse tan of 24 over 7, which is 73.74 degrees. So we can use this angle to give the direction of ship B as seen from ship A. We could also have used this angle here, but normally we get the angle measured from the positive x-axis. A and B can exchange signals when they are not more than 20 kilometers apart. At what time can they begin to exchange signals? Here I've shown the moving axes, x prime, y prime, whose origin is at A. So A, of course, is moving, so the axes are moving. Initially, that is at t equals 0 or 12 noon. Ship B is 50 kilometers south of ship A. We've also worked out the velocity of B relative to A. It is in this direction. It is 7i plus 24j, so this is the direction roughly. So this will be the trajectory of ship B as seen by ship A. So it will travel at constant speed along this straight line because its velocity is constant. This is VBA. We are going to be interested in the situation when the ships are 20 kilometers apart. So initially they are 50 kilometers apart. So B appears to move along this trajectory as seen from A. So at some time B is going to be 20 kilometers from A. So this distance here is going to be 20. And that will happen at a second time. So at some other time B will also be 20 kilometers from A at a second time. When the ships are 20 kilometers apart, or less than 20 kilometers apart, then the ships can exchange signals. So the ships can exchange signals when B is along here in its path. When it's here, it's more than 20 kilometers from A, and when it's up here, it's more than 20 kilometers. So we will be interested in this distance. Well, actually, more specifically, we're interested in the times for which the ships are we're interested in the interval of time for which the ships can exchange signals. So we will be interested in the time when ship B is here and the time when ship B is here. And by subtracting the two times, we can find the interval of time for which the ships can exchange signals, for which the ships are less than 20 kilometers apart. So the ships will be less than 20 kilometers apart when B is along here. We are going to start by finding distances. This blue triangle is isosceles. These two sides are the same. So the shortest distance of A to the path of ship B will actually bisect this line here. So this line that I've just drawn in is the distance of closest approach of the two ships. So this line is the perpendicular distance between A and the path of B. What we can do first of all is calculate this distance, because once we know this distance, we can use Pythagoras to find this distance here, because we have a right angle triangle formed here. So how do we find the distance of closest approach? Well, we use the fact that this triangle here, this big triangle here, is right angled, this green triangle, and we know this angle here. We know this angle because we know this vector. We saw earlier that vector VBA makes an angle of 73.74 degrees with the horizontal. That was just inverse tan 24 over 7. So knowing this angle here, we can find this angle here. This angle is actually got by taking 73.74 degrees from 90 degrees, because 73.74 degrees is the same as this angle in here. This angle here is also 73.74. These are vertically opposite angles, so these angles are the same. And of course the three angles in this white triangle, I'm actually looking at this triangle, add up to 90. So if this is 73.74, then we have to take from 90 to find this angle here. Knowing this angle, I can now find D, which is the distance of closest approach. So we have this right angle, this green triangle is right angled, so we multiply the hypotenuse, which is 50, by the sine of 16.26, and that gives us 14. And this distance is in kilometers, because this distance between A and B initially is 50 kilometers. Now we can apply Pythagoras' theorem. So now we can go back to, well, we can start to look at this right angle triangle here. The hypotenuse is 20, D is 14. So if we want to find distance from here to here, which I'd call R, we just use the fact that 20 squared equals 14 squared plus R squared. So R is the square root of 20 squared minus D squared. Well, D is 14. That gives us 14.283 kilometers. Now we're interested in the time that they can begin to exchange signals. So we want a time taken for ship B to go from here to here. So we need to find this distance here. Well, what we can do is use Pythagoras to get this distance here, which I will call L. That's the distance between B at time t equals 0 and the point when B is at its closest distance to ship A. So we can look at this triangle here. We see that it's right angled, of course. The hypotenuse is 50. This side here is 14. We just calculated D earlier is 14. So we can find L by Pythagoras. So we see that L is the square root of the hypotenuse squared minus this short side squared. We get 48 kilometers for that distance, and now to find the distance of B to this point here, we just take 48 and subtract R, which is 14.283. So we get 33.717 kilometers. Now we need to find the time taken for the ship to go from here to this point. We have the distance, so we need to get the speed of B relative to A. We worked this out earlier. We had vector VBA, we got its magnitude, and its magnitude is the speed of B relative to A. So we have the speed of B relative to A, and we have the distance, so now we can find the time. So we're just dealing with constant speed here in a straight line. We know that speed is distance over time. So we're interested in getting the time. So we just interchange these. So time equals distance over speed when we're dealing with constant speed. So we have the distance, which is in kilometers, so 33.717 kilometers, divided by the speed, which is in kilometers per hour. These kilometers cancel. 1 over h to the minus 1 is just h to the plus 1, or just h. So the time comes out in hours. So we get 1.3487 hours. So that's the answer to this part here. That's the time taken for the ship to get to here. So then it can send a signal to A because it is now at a distance of 20 kilometers to ship A. So now we want the time interval over which the ships can continue to exchange signals. So we want a time interval for the ships as ship B travels from this point here to this point here. So by symmetry, the distance from here to here is 14.283, and the distance from here to here is also 14.283, because this is an isosceles triangle, sides at 20, and this here is the perpendicular in the isosceles triangle, and the perpendicular bisects this line here. So the distance of here to here is also 14.283. So to answer the last part, we get the total distance from here to here, which is just 2 times 14.283, or 28.566 kilometers, divided by the speed, which is constant, which is 25, speed of B relative to A, and we get 1.1426 hours.